Hey guys, Sammy's back. And we're on to valid Sudoku. I looked through the rest of the path and man, it seems like such a journey. I'm so freaked out. Like, there's so many more questions to try and understand. But I am excited to just plug along and expose my brain to as many new patterns as possible. I'm not too concerned about getting the right answers. I'm more concerned about exposure, because the more exposure under various loads, the better I will be able to recognize different patterns. So let's get into valid Sudoku. And I've played Sudoku before, so that helps. But we're gonna have to do it. We're gonna have to program a way to understand if a Sudoku board is valid. So only this is probably the last one I'm gonna do today, and I'm just starting to get fried because I've already spent like an hour and a half on problems today. So only the filled cells need to be, I've done 2 mediums. Only the filled cells need to be validated according to the following rules. Each row must contain the digits 1 to 9 without repetition, and each column must contain the digits 1 to 9 without repetition. So row, column, and each of the 9 3x3 subboxes of the grid must contain the digits 1 to 9 without repetition. So all these. So a Sudoku board partially filled could be valid, but is not necessarily solvable. Interesting. Only the filled cells need to be validated according to the mentioned rules. And you have the ugliest array I've ever seen, where we have periods to tell where there's nothing and integers to determine where there are numbers. Output is false. Explanation, same as example 1, except with 5 in the top left corner being modified to 8. Since there's 2 8s in the top left sub box, it is invalid. I like that. Wow, that's a lot of people. So I really don't know what to do, but we're given a board. So we just have to we have to find a way to define this board. And to do so, we can we just want to be able to create a cross-reference between each column, row, and 9 sub boxes. So like the first thing we can do is check if there's any duplicates within each of these boxes, and any duplicates within each column, and any duplicates within each row. Is that it? Because all we're doing is without repetition. Is that it? Is that really it? That can't be it. There's some more stuff to it. So there has to be more to this, where we have each row and each row and each column, and we have these digits 1 to 9 without repetition. So I'm just trying to think. Is that it? 1 to 9 without repetition, 1 to 9 without repetition, 1 to 9 without repetition. Is that it? Maybe that's it. All right, we can start to define the columns. We can start to define the rows. And we can start to define the squares. And we're going to do this with our handy dandy friend, the dictionary. We're going to create some empty dictionaries with this command, collections.defaultDict and set. And from here, what we're going to do is just look if, oops, we're going to look in the range of 0, well, I guess it's not 0 to 9, it's just 1 to 9. If, oops, well, we have a row. We just want to go through every row and every column. So for every row and for every column, we have our board, right? Which is this. For every row, we go like this. For every column, we go like this, down, and say if it's empty, if we see a period at this position, so we're just doing a nested loop. If it is empty, then we can continue. But if it's not, we can set up some conditionals such that we can check if there are any duplicate values. So if this particular position of the board is in rows as we're iterating through it in the dictionary, or if this position of the board is in columns as we're iterating through it, or if this part of the board is in the squares as we are within each square, which we have to determine with this multiplication, or this mathematical thing. I need to find a word for that. We can return false because we can check. Because we're checking for the duplicates. Otherwise, for the columns, we can add the board R and C, the position that we are at the board for the columns of C, and for the rows of R, we can add the current position of the board, and then for squares, we can add the position. For squares, we can add this position of where it is in the square and add it to the board. Or no, we can add this position to the board to squares. So it's basically an empty, we're assigning this to empty, to the empty dictionary as key value pairs. Oh, I see. So for rows of R, we have our dictionary that we initialize up here, we have a dictionary. And if it exists already, then we return false. If it doesn't, then we continue. And if we can make it all the way to the end, then we return true because it is a valid Sudoku board. So we don't even have to solve it. We just have to check if there's no repetition. And if there's no repetition, it's valid. But let's break this down a little bit more to understand what's happening. So for every row in range 1 to 9, and for every, or is it range 0 to 9? Or it'd be 0 to 8. 9 is just yes, I believe that's correct. So if board R and C is this, continue. If board R and C is in rows R, which is our dictionary, then we can return false. If this position that we're iterating through on the board is in the columns C, then we can add this. So we're just creating a key value pair for every board that exists, or for every position of the board that exists. So like 0, 0, that becomes a key value pair for this value. I believe that's correct. So if this would be at calls of 0, we add 8. At calls 1, we add 3. At calls 2, we add 0. At calls 3, we add 0. At calls 4, we add 7. And what we're doing with this as we go to the next, or no, it's not like that. It's for this key value pair, I believe, because it has to all be different. They all have to have different key value pairs based on this, because we don't want, we can have duplicates from here, from column, or from, say, row to row. I was looking at columns, not rows, but row to row, we can have duplicates. But there needs to be some kind of distinction that I'm trying to figure out. So the dot add is a new key value pair where it's something is being added. There's something I'm missing here. It's like how it's being assigned. It's like the count at some instance here, not how I think it's working. It's like it's counting. It's not telling the exact position.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem valid Sudoku, and I'm going to be recording this on the 4th of July, so hopefully there aren't too many firework noises in the background. So we are given a 9x9 Sudoku board, and all we want to do is determine if the board in its current state is valid or not.
Okay, I determined that.
A row or any particular 9 of them, as you can see.
Okay.
So basically that both need to be in this position. So in this case, this is not a valid Sudoku board, right? Well, that's technically true, but for this problem, we are going to consider this board, yes, it's valid, because as of right now, based on what the cells are filled in, like what cells are filled in, there aren't any contradictions. We're not going to assume anything for any of these empty positions, even though we know for sure, yes, a 9 would have to go here based on this row. We're not going to assume that. So it's actually a little bit easier than you might think. So the algorithm is going to be pretty standard, right? We're going to go through every single row and make sure every particular row does not have any duplicates. How could we do that? We could do it a bunch of different ways, but I'm going to do a hash set, right? So a hash set will be easy for us to detect if there are any duplicates. So we're going to have a unique hash set for every single row in the entire grid, right? So then we can easily determine if any particular row has any filled in duplicates, right? This row obviously doesn't. A 5, a 3, and a 7, no duplicates, right?
No.
So that portion is pretty easy, right? Number 1 is pretty easy to check. What about number 2, checking each column? We can do the exact same thing. Just have a hash set for every single column, right?
Yes.
Every time complexity. Now, the last part, in theory, should also be pretty easy, but coding it up is a little bit more tricky. There are many ways to do it. I'm going to show you the easiest way. We want to be able to tell, okay, for every 3x3 grid, which there are 9 of, does any of them have any duplicates? So again, we can use a hash set to represent each of these 3x3 grids. But the question is, how are we going to do it? How can it be easy to code something like that? And that's what I'm going to quickly explain to you right now. And after I do, we can jump into the code. The overall solution is yes, though, going to be O of n 9 squared. We're pretty much just going to have to iterate over the entire grid and nothing else. But we are going to have extra space, also O of 9 squared, because we're going to have 3 hash sets, which are going to be this exact size. So roughly, this is the memory complexity as well. So we want to represent each of these 3x3 grids with a hash set. But how do we know if we're at any particular value, right? Like I have labeled the indices, right? This is going to represent what row. This is going to represent which column.
Yeah, that makes sense.
How do we know if any particular value, such as 1, 1 happens to be in this 3x3 grid, where this 3x3 grid, how can we differentiate them? Notice how each of these 3x3 subsquares happens to be 3x3, right? So one way is to basically make it so that we can have an index, right? So maybe 0 represents this row of the 3
I'm just waiting
different
I'm waiting for it
right?
to click.
And a 1 represents this row of 3 squares, and a 2 represents a row of this, right? And similarly for the columns, right? A 0 over here represents this column, a 1 over here represents this column, and a 2 over here represents this column.
Yes.
Then if we had 2 indices, right? If we can somehow take 4, 4 and convert it to 1, 1, then we know it goes inside this subsquare, right?
Yes.
So basically we have 9 different subsquares. We're going to have indices to represent them, right? A 1, 1 means that this is the subsquare that we're talking about, right? This 1. And the way the math is going to work out is since each of these is 3x3, we can just take the actual index, such as 4. Let's say we were given 4, 4, right? This is the square we're talking about.
Oh, and then we do like the modulus.
4, which is the row, divide it by 3. Integer division, right? We're talking about integer division. 4 divided by 3 is going to give us a 1. We do the same thing with the column.
Not
right?
modulus, because we're just trying to see how many times
right? So if we
it
take
fits
the actual
in
coordinates 4, 4,
the bigger
divide
number,
the coordinates
or the smaller
integer
number,
division by 3,
or into
then
the
we get
numerator.
the index for the row column, and it basically identifies which square this is a part of.
That's
now,
what the
let's
two
just check that the edge cases work out. Let's try 8, 8, right? This is the
forward
boundary.
slashes are.
What happens if we take 8 divided by 3 and 8 divided by 3, right?
Yeah.
Well, then we get 2, 2, right? Integer division, we always round down 2, 2. That works out for us, right? Let's do a different edge case. Maybe we try this square, right, on the boundary. Does this identify 0, 0? Because that's what it should. Well, let's take the positions, the indices, 2, 2, divide them by 3, 2 divided by 3, 2 divided by 3. We round these down, so we get 0, 0. That does uniquely identify, or it, correctly identifies that it belongs to this 3x3 grid. So that's kind of how we're going to identify when we go through every position, every cell in the entire Sudoku board, which of the 3x3 grids is it a part of, and then we can add them of values, the row column, not the actual row
Yeah,
column,
that's what
right?
I'm saying.
When we convert it to the row column, basically row divided by 3 and column divided by 3. That's what the key of the hash map is going to be. And the value is similarly going to be a hash set, where we can tell, do we have any duplicates in this 3x3 grid or not, right? Same for every single 3x3 grid. We're just checking, does it have any duplicates? If not, then we can continue. If it does have a duplicate, that means our Sudoku board is not valid, and then we would have to return false. But if it is valid, we're just going to continue. So we're basically going to go over the entire grid, right? Every single position in the entire grid. If we find any duplicates, we return false. If we don't, at the end, we can return true. So now we have enough information to actually write out the code. So let's do that. Okay, so now we can write the code. Like I mentioned, I'm going to be detecting duplicates with
I just want to know
hash set or dictionary, just because it's easier. Divided by 3 and column divided by 3.
That's the integer
so
division.
That tells us the current square that we're in. And this will return a set, as you can see up above, of all the values that we have seen in the current square before. And if this value that we're at right now is a duplicate, that means it's already going to be in this hash set, in which case we can also return false. So this is basically our way of validating that this current Sudoku board is valid. If we have any duplicates, that means it's not valid. We return false. If it is valid, we continue, and we basically update all 3 of our hash maps up above. So columns of the current column, we're going to add to it the current character that we just saw. And we're going to do the same thing with the current row that we're in. And we're going to do the exact same thing with the current square that we're in. Of course, this has a pair of values as the key. So this makes sure that our hash sets are updated, and we'll make sure to detect any duplicates when we get to the next iteration of the
But I want to know.
So in this way, we're iterating over the entire board. And if we never detect any duplicates, then we can, outside of the loop, just return true. That means the current Sudoku board.
But I want to know what the hash set looks like. So time to play with my food a little bit. What does that mean? Oh, I need to import collections. let's see. We have our default dictionary. So this is the first iteration. I don't need to go through here because that's just my if statement. So calls value of 5 at 0. I just want to know what will happen. Seven, 9. Oh, okay. 3 rows. This is rows. 3, 7, 5. Row 0. 3, 7, 5. So it's just checking 6, 8, and then this will become 9. What? Where is 4? Oh, this is a 6, 8, 9. 6, 8, 9. What am I missing? I'm just trying to figure out how these key value pairs work. 3, 7, 5. 3, 7, 5. 5, 6, 9, 1. Five, 6, 9, 1. Then we have 9, 8, 6, 8, 6, 3, 4, 8, 3. I think it's just how it's iterating through the list. Because it's going through rows first and then columns next. So then this will add 1 to this. What? It did not add 1 to that. What am I missing? 0, 1, 2, 3, 4, 5, 6, 7, 8. So it should be 0 to 8. I wonder what the difference is between 0 to 8 and 9. Like, will it make a difference? Five, 3, 7. Go to the next one. 6, 1, 9, 5, 9, 8, 6, 8, 6, 3. Go to the next one. 4, 8, 3, 1. Okay, I think that made a difference. But why does that make a difference? I wonder if it doesn't. It doesn't. It skips. 1, 2, 3, 4, 5, 6, 7, 8, 9. Why does it have to be range to 9? Why does this have to be range 9 and not range 0 to 8? But why does it exclude the last row and last column? Is it because it's a dictionary? What is range 9? Integer values. Oh, wow. 0 to 9? Why does it go to 9? Okay. So you can't go 0 to 8 because 8 is exclusive. That makes sense. So we have all this. So I want to know why this is like this. So we have columns here. And we add to board RC. So we're on 0. Oh. So we have a key value pair of the column that we're at. And we add to where every column is. Yeah, that makes sense. That makes sense. So for every row, we have each row as determined by the key value pair of the row, not necessarily the exact position of the board, because we're just looking for the key value pair of the row. And because we're only going through each row at a time, then we're able to check if there's any duplicates before moving on to the next one. Oops. Thank you.